This video is on the objective, conduct and interpret a chi-square goodness of fit test. Okay, and this is a video where we're going to go through all the steps of a chi-square goodness of fit test, right, to determine if a certain set of data, has a good fit, a significant fit to a given distribution of data. Do the data fit a uniform distribution, or a binomial distribution, or a normal, or something else. Alright, so again, if you want to read more about it, click on More Instruction, look at their videos, their notes, their examples. Hopefully those help you. In fact, I am going to go over some of that so I don't have to write it out. Alright, so the chi-square goodness of fit test. Alright, so remember, in this type of hypothesis test, you determine whether the data fit a particular distribution or not. Right? For example, you may suspect your unknown data to fit a binomial distribution. You use a chi-square test, meaning the distribution for the hypothesis test will be chi-square, to determine if there is a fit or not, right? If there's significant evidence to claim that they fit or not. So the steps of completing a chi-square goodness of fit test are the following. So remember, one is your hypotheses. Now the null hypothesis and alternative hypotheses for these will be the same every time. The null hypothesis is what we're going to assume is true, and then decide whether or not to reject that later. The null hypothesis will be that the variable has the specified distribution. All right, we'll assume that our data does fit the given distribution. And then the alternative hypothesis will be the opposite of that the data does not have the specified distribution or does not fit. Step 2 is decide on the significance level. Right, what's the value of alpha? Right, this comes up in every hypothesis test. Step 3, compute the test statistic, right, that chi-squared value. They're calling it chi-squared sub 0. And I'll refresh your memory as to how to calculate that. Step 4, determine the degrees of freedom and find the critical value to reject the null hypothesis or not. Right, we're going to do a critical value approach. And I can also show you I'll also show you a p-value approach as well. We'll do both, and you'll see that both of them will give you the same results. You'll reject the null hypothesis in both. You'll fail to reject the null hypothesis in both. And finally, make a decision about the null hypothesis. Do you reject it or not? And interpret the results. Your final conclusion will basically be, yes, the data do fit the distribution, or they don't. Right, and there's evidence to support one or the other. So again, these steps look similar to other types of hypothesis testing. However, the main differences are the null and alternative hypotheses, right, which is the same for all goodness of fit tests. All right, and the computation of the test statistic. Hopefully you recall this stuff. Right? Again, this was in a previous objective, or another objective in this assignment, on calculating the test statistic, where I take each observed value minus each expected value, square that, divide by the expected value corresponding to it, and then add all those up for every category. The goodness of fit test is, we'll use a right-tailed test. Right? It says almost always right-tailed. We're going to be doing right-tailed tests. Every single one of these will be a right-tailed test that we come across, unless they say otherwise, but I'm pretty certain that all of these are right-tailed. If the observed values and the corresponding expected values are not close to each other, then the test statistic can get very large and will be way out in the right tail of the chi-squared curve, and therefore we'd probably be rejecting the null hypothesis. And if they're close to each other, right, if the observed data, what actually happened, and what you expect to happen if the data fit the distribution, if they're close to each other, then the chi-squared test statistic will be small or smaller and most likely not be in the right tail rejection region, and you won't reject the null hypothesis. All right, and then they go over an example here, and I'll let you read the examples, and watch the videos and whatnot when you go through more instruction on your own. So let's get into a problem. All right. So here, a professor is trying to determine if her students guessed on a certain multiple choice question. She expects that if the students guessed, the distribution of answers would be uniform. Right? If she suspects that they guessed, she'd expect that every answer would be guessed about the same number of times, right? Uniform across the board. So she compares the observed distribution of answers with the uniform distribution. All right, so, and the question is, she's trying to see, did what she observe, did what her students actually answer fit reasonably well into a uniform distribution? The professor conducts a chi-square goodness of fit hypothesis test at the 5% significance level. All right, so first we're asked to set up the hypotheses, right? So again, I'm going to write this stuff out on a piece of paper, and we'll go through step by step the chi-square goodness of fit test. Okay, so here's the table that was given. And these are the answer choices for some questions she suspects they guessed on, or tries to determine if they just all guessed on it or did most of them know it. Now the observed data is what actually happened, right? This is the data, and this is what actually occurred, right? What actually happened. Now the expected counts of 12 each. Well, notice, when you look at the observed counts, 12 of her students answered A for that question, 9 of them answered B, 5 answered C, 22 answered D. The total number of students that answered this question then are 48. Right. Now, the expected counts, these expected counts are, well, what if we assumed that the distribution was uniform, right? She's trying to see if the observed data fit a uniform distribution. So if uniform, if it were truly uniform and I had 48 students, and there are 4 categories here, 48 divided by 4 is 12. You'd expect 12 in every single category if it were uniform, right? The same across the board. All right. So our hypotheses. The null hypothesis again is that the students' answers, the observed distribution the distribution of the student's actual answers fit. They do fit into, or they're significantly close to, a uniform distribution. Okay. And again, this is being assumed here. Right? And if I assume this, then that's where these expected counts are coming from. Right? What would you expect the counts to be if you had 48 students and you assume the distribution of the answers was uniform? You'd expect 12 of them each to 12 each to answer these A, B, C, or D. All right, then the alternative hypothesis is that it doesn't fit. Right? The observed distribution, the distribution of her students' answers, I'll just say observed dist for distribution, doesn't fit. Right? Does not fit a uniform distribution very well. right? It's actually, pretty far off of it. Okay, so that's part one, right, where we're just asked to set up the hypotheses. So the student's answers have a uniform distribution is the null. And the student's answers do not have the uniform distribution is the alternative. Okay. All right, then we'll have to, again, we're just like other objectives where you asked to complete the steps, there's going to be more to this, right? Then they ask us to compute the test statistic rounded to 3 decimal places. All right. Well, first, let me give me alpha, right? Step 2 is the significance level. All right, alpha. They said, the significance level for this test was 5% or 0.05. We'll keep that in mind. And now I would like to calculate the test statistic for our data. All right. Now this was, again, in this same assignment, this is done in another objective, so I have other videos on this as well. The test statistic is, a chi-squared value, and they call it, they're calling it chi-squared sub 0 or chi-squared sub test. And here's the formula they're shooting at you. It's the sum over all value, over the k values, where you're taking every single observed value minus its corresponding expected value, squaring that, and then dividing by that corresponding expected value. So observed minus expected squared divided by expected. K is just the number of terms in the sum, which is the number of observed values, or the number of expected values. So K here is 4. There are 4 observed values, 4 expected values. K is 4, and this is like the number of categories. In this case, in this particular example, it would be the number of answer choices. All right, so what we're going to have here are there are going to be 4 terms in this sum, and here's how it would be set. Here's how it's set up. So let's go one category at a time. So for the answer choices of A, there were 12 students answered A, minus, and then if it were uniform, you'd expect 12 to answer A. So I take 12 minus 12 squared divided by 12. All right, observed minus expected squared divided by expected for that first category, for the answer choice of A, plus, and then I do the same thing for the next category, the answer choice of B. 9 students actually answered B. Take that away, subtract the 12 you expected, squared divided by 12. Plus, and now for answer choice C, 5 actually answered C, minus the 12 you'd expect, squared divided by the expected of 12. And then finally, the fourth category, answer choice D, 22 answered D, minus the 12 that you expected, squared divided by 12. Okay. Now, you can do this by hand or punch this all in a calculator here. I'm eventually going to use a calculator. But every single one of these is over 12, so denominator is 12 at the end here, common denominator. And the numerator is 12 minus 12 squared, that'd be just 0 squared. So there's no real reason, there's no real need to write that, but 0 plus, and then negative 3 squared is 9, plus negative 7 squared would be 49, plus, and then 10 squared is 100. Alright, so I'm getting here my test statistic, this chi-squared sub 0 or chi-squared test, is that's what, 158 divided by 12, which I will round. Alright, so I'll pull up the calculator here. 158 divided by 12. So that's 13 and 1/6. So 13.16, and then they said round to 3 decimal places, so it's 666. So 6 would round this up to 13.167, right? So approximately 13.167 is my test statistic, my test chi-squared. All right, now that's one way to find the test statistic by hand. Another way is to use your calculator and some lists. All right, again, I've shown this in other videos. If you go Stat, Edit, and then down, say L1, list L1, I'll put the observed counts. So we have 12, 9, 5, and 22. And then down list L2, I'll put the expected counts. So just a bunch of 12s. Alright, then over in list L3, I'll move my cursor up to where it says L3, hit enter, and then enter a little formula. And what I'm going to enter is this observe, all the stuff we're adding in the test statistic calculation. The observed minus expected squared divided by expected. So in parentheses, now the observed counts in my list were down L1. So I'm going L1 minus the expected counts were down list L2. And then we're squaring this and then dividing this by, L2. Now I could have also just not put in L2 and just had L1 minus 12 squared and then divided by 12. But I already entered them, so might as well. So there's the observed counts minus the expected counts all squared and then divided by the expected counts. Then when I hit enter, you see these four values here. And then the test statistic is the sum of these four values. So to find that, right, let's get out of here, quit. And if you want to do some math, like add up a list, go to above the stat button, you hit second stat, go to the list menu, over to math. Number 5 is the sum of list L3. Right, L3 was that observed minus expected squared divided by expected. And you see I'm getting the same thing. Okay. So that was an alternate method of finding the test statistic. All right, and there's a third way, but I'll get to that later, right, where you can actually run the whole goodness of fit test with your calculator. But I'll get to that a little later. All right, so 13.167 when rounded to 3 decimal places. All right. Great. Continuing on. Next, they ask us for a critical value. All right, determine the and this is a right-tailed test. Right, all these chi-squared tests that we're going to run are right-tailed tests. All right, so first I need to all right, so we set up the hypotheses. We got the test statistic now, 13.167. Determine the critical values using the following table. All right. So I need to know the numbers of degrees of freedom for my chi-squared distribution. All right. So we're looking at here the degrees of freedom will be k minus 1, and this is for the goodness of fit tests, right? The GOF test. And this is actually going to be different for all the different kinds of tests, chi-squared tests you're going to do. There's the goodness of fit, there's the test for independence, test for homogeneity, right? So for the goodness of fit test is k minus 1. Now k, remember I said earlier, was the number of categories. All right, so I know there are 48 students, but there are only 4 categories that I broke the students up into, those that answered choice A, B, C, and D. So we're looking at a chi-squared distribution with 3 degrees of freedom. All right, and I'll draw a little picture of that. All right, remember chi-squared starts at 0, And then you have your values of chi-squared on the number line here. And it was now with 2 degrees, 2 or 3 degrees of freedom, I could pull up a calculator and look at this. But remember, it was it was bulky on the left and skewed right, so something like that. I don't know. All right, I could pull up a calculator and draw a better picture. The mean was 3, right? The mean was a little bit to the right of the peak, so maybe here. The mean value was 3, and the standard deviation was the square root of 2 times this number of degrees of freedom, so the standard deviation would be a square root of 6. All right, but what we're looking for is, again, always right-tailed, these tests. What we're looking for our significance level, again, was 5%. So what I want to find is what's the chi-squared value that has an area to the right of it of 5%. And that would be labeled as chi-squared with a subscript of 0.05, right? Kind of like z-scores and t-scores. So what's the chi-squared value? So what's this? This is a critical value then. This is the entrance to my rejection region. So which chi-squared value for this, chi-squared distribution with 3 degrees of freedom has an area of 5% to the right of it? Well, again here, 3 degrees of freedom. Looking at this row. And we're looking for the chi-squared value that has, 0.05 to the right, 5% to the right. So 7.815. So back on my drawing, this is a chi-squared value of 7.815. All right. And what was our test statistic? It was 13.167, which is way over here. Right. 13.167. This was our chi-squared sub 0, right? Our test statistic. That's definitely in the rejection region. And that tells me that the observed distribution is too far away from the expected distribution for us to consider it uniform. All right, the observed distribution is too far from being a uniform. All right, so we're going to end up rejecting the null hypothesis that the observed is a uniform or fits a uniform, and say that it doesn't fit a uniform. Right, we'll go with the alternative. But let's enter the critical value, 7.815. All right, 7.815. And again, the degrees of freedom is the number of categories minus 1. Then our decisions, right? Like I said, we reject the null hypothesis, right? We should reject the null hypothesis because our test statistic is definitely beyond this critical value. All right, and then going back looking at my hypotheses, right, the hypotheses were, again, the null was that the observed distribution fits a uniform. We are rejecting this, meaning we're accepting or leaning toward or supporting the alternative. So we conclude that the evidence shows us at the 5% significance level that the observed distribution doesn't fit, is too significantly far away from a uniform distribution. Right. So at the 5% significance level, there is not enough evidence to conclude the students were not guessing. Oh, okay. Ooh. Remember the uniform distribution was they were guessing. Right? She thought there'd be a uniform distribution if they were just guessing. So the null hypothesis that the observed distribution fit uniform means that they were guessing And if the observed distribution did not fit a uniform, that means they were not guessing all of them, right? Some of them actually knew the right answer or knew how to figure out something. So we would say that there is enough evidence to say that they were not guessing. So this one here, right, at the 5% significance level, there is sufficient evidence to conclude that the students were not guessing, right? It wasn't fitting a uniform distribution. Okay. Great. And very similar to a lot of other videos you've seen where you're going through all the steps of a hypothesis test, you see how it said that the objective was done? Yeah, if you get through one of these fully without getting anything wrong, that objective will be over. Now, let me show you also how to do this on the calculator, how to run this goodness of fit test. So you remember my lists from earlier? So stat, edit, remember down list L1 were my observed values. Down list L2 were my expected values. Well, if you've got those lists entered, you can go stat, hit the stat button, go over to tests, and then scroll way down. Now, I know the 84s have this. I don't remember if the 83s do or not. But you see here at D, see there's this chi-squared GOF test. That's chi-squared goodness of fit test. I click on that. It says, what's your observed list? Well, that was L1. I already have L1 there. What was your expected list? L2. I already have L2 there. And then what was the degrees of freedom? Again, that was the number of categories minus 1, which, it's already 3 from a previous problem I did, but 3 in this case again. Again, this might change, but then I go calculate, and you see look at that. This is the third way you can find the test statistic. You have your observed list, your expected list, and then you go to this chi-squared GOF test, goodness of fit test, and you see the very top line gives you the test statistic, 13.167. The next line gives you the p-value. Now look, the p-value, remember the p-value would be the area to the right, being that it's a right tail test. All right. I'll draw that here. If I was doing the p-value method, I'd find where's my test statistic, 13.167, and then find the area to the right. Area to the right of, chi-squared, or test statistic, that would be the p-value. And they're telling us here the p-value is pulling the calculator back up, 0.004. And this is definitely less than or equal to alpha. And if that's the case, remember, if the p-value is less than or equal to alpha, you reject the null hypothesis, which we said we would do anyway because, the test statistic was in the rejection region. So you can do this, you can get the same result, reject the null hypothesis, with the critical value method or the p-value method. And the p-value comes up in the calculator when you run the chi-squared goodness of fit test or GOF test, like that. Okay. Now the only problem with this is, this doesn't give me a critical value. So you're going to have to look at those tables that they give you for the critical values. But other than that, this is pretty good at giving us p-value, and then you can compare the p-value to alpha and see whether or not you'd reject the null, and then when you reject the null or not, then you make a conclusion. All right. Okay. So lots of steps, longer video than usual, but usually these completing the steps of a hypothesis test are longer videos. And I'm hoping that watching me go through this, on paper, on the calculator, reading through the answer explanations when they come up, looking at the more instruction, looking at their videos, their notes, their examples, all this stuff. I'm hoping all this stuff helps you when you're going through this material on your own. And thank you very much for watching.